This terminal explains about the graph of piecewise function that relates with the real life of human being. So consider we have we have three tones, or we have here uh, CTA, and I have again CTB, I have again CTC. Then here I have yellow car starting coming from CTA to this one, to this bridge. But this bridge is broken or somewhat it has a hollow. So this yellow car can travel from CTA to this broken bridge. Same is true. This car comes till this one, but it can be curved or turned to this position because this bridge is broken or it has hollow, and again it cannot be turned this one, but it's starting from this one to CTB, it is continuous. Same is true from CTC, I have CTC here, then the car moves to this direction until this. Then such real life examples are related with the piecewise graphs, or mathematically we can draw in such this one. So simply a car starts from, so this can be translated or explained using the mathematical graph. So from this one, started from CT8, this one until the broken bridge, then from CTB until the broken one, until this one, which is continuous, or the car can move as you want as like, and starting from this one, CTC. So this real life condition can translate mathematically into this one. So this is the terminal graph of piecewise function that could be related with the mathematical graphs. Which says, given the piecewise graph of f of x as shown below, hence determine whether the function f of x is continuous at x equals to minus 2, x equals to 0, and x equals to 3. The piecewise graph looks like as shown this one, which in a sense, such graph is called the graph of piecewise functions. So we are going to be checked at x equals to minus 2, at x equals to 0, and at x equals to 3 instance, whether this function is continuous or not. So, as you know, a function is said to be continuous. It should be satisfied three. First, the function should be defined. Second, the limit of f of x as x approaches to a should be exist, which means that its limit is said to be exist if the right hand side and the left hand side have the same value. At that time we'll call the limit of the function is exist. If it is exist, it is equals to with the functional value. So if it satisfies these three conditions, at that time we'll see, or we'll say the function is continuous at n number a. So having this definition from the graph, we are going to be check whether this graph is continuous at x equals to minus 2 or not. Now, if we encounter such graph, Is it defined at -2? We'll check it. Now look, we have two values. When you look to the above, which is equivalent to, then f of -2 is 2. So when you look to the below one to this direction, it is equals to with minus 1. So if you ask someone what is the value of f of -2 instance, you are going to be select the solid one. You have the endpoint. The endpoint for this graph is here, which is solid. But the end point for this graph is it has hollow. So we'll reject for the hollow one. So we'll take for this. So now, is it defined? If f of a is defined, yes. F of -2 is 2, which is defined. Okay. Second one, we need to check the existence. Checking the existence, in a sense, you are going to be evaluate the limit from the right hand side and the left hand side. So, what is the limit of the function as x approaches -2 from the right, which is -1? And which means that, look, when you look at the graph here, when you approach from the left to -2, the value is -1. As you approach from the right, mean that through this position to -2. So the graph or f of x will approach to -1 again. When it approaches from the left to -2, the value is 2. The value is 2. So it has different values. At that time, we say the limit is not exist. The limit is not exist, which means that the limit from the right is -1, and the limit from the left is 2, which means that the limit from right and left is different, which is not exist. The third criteria, if the limit is not exist, the limit and functional value are automatically different. At that time, the function is it defined? Yes, defined. But the limit is not exist. If the limit is not exist, it has different value. The right and the left have different values. If they have different values, the limit is, we will say, not exist. And the limit and the functional value are different. The functional value f of -2 is 2, but the limit as x approach -2 is sometimes -1, sometimes 2, which are different. So at that time we say at x equals to -2, at x equals to -2, the function is not continuous. Function is not continuous. Hence f of x is not continuous at -2. Such graph is called jump discontinuous. Such graph is called jump discontinuous. Let's see for the example. For this graph, is it continuous at x equals to 0? For this value, 0 is just around here. So we'll check it. Is it defined at f of 0? Yes. F of 0, if you evaluate f of 0, you have 1, or the coordinate you have here 0 and 1. For x value 0, but for f of x or y value 1, which is defined. Again, we need to check the existence. What could be the limit when we approach from the left to 0. The left to 0. What could be? To which number the function is approached? To 1. It approaches to 1. Again, what could be the value when the function or as x approaches 0 from the right? From the right. Yes, from the right. Again, the same is true, 1. Therefore, the limit from right hand side and the limit from left hand side are equal. At that time, the limit is called exist. The limit is called exist. Is from hand side, and as you see from this note, the right and the left are equal, which have same value, which is 1. If the limit is exist, the limit and functional value are the same. The limit for this one and functional value at f of 0 have the same value, which is 1. So it is defined at f of 0. Again, the right hand side and the left hand side limits are equal. At that time, we say that the limit is exist. If it is exist, again, the limit and the functional value are the same. Therefore, it is continuous. Hence, it is continuous at x equals to 0. At x equals to 0. Okay. We remind to check at x equals to 3. At x equals to 3. Okay. Please observe carefully. Number 3. Number 3 is here. But around here for the graph, it has hello. Which have an hello. Straight downward, here is a point again, which is solid. For this value, which is solid. At that time, corresponding to number 3, please forward. Be careful. At exactly number 3, we have two values, 3 and 0, but here is 3 and minus 1. In short, this tells you or indicates you the limit is not exist. As x approaches to 3 from the right, which is 0. As x approaches from the left, the limit is minus 1. The limit is minus 1. So from the different positions, it has different values. At that time, we say the limit is not exist. From different, if we have from different direction, the same value. At that time, we say the limit is exist, but now it is automatically different. Sometimes it is 0, sometimes it is minus 1. So let's check anyways using our criteria. The first one, it is defined, yes. F of 3 is 0, yes. We need to check the existence. Checking existence in a sense, please find the limit from the right and the limit from the left. From the rest, as I have told you, which is 0. From the right, you have minus 1. Automatically, they have different values, which is not exist. If it is not exist, the third criteria will be violated. It violates the third criteria, would mean that the limit of the function f of x, which means that from the right and the left, is different from the functional value. At that time, this function is defined, but the limit is not exist. If the limit is not exist, the limit and the functional value are different. Hence, f of x is not continuous at 3. Again, such graph is called jumped discontinuous. So if we summarize these all examples for the jumped one, if you encounter such graph, when you look for this one, for example, at x equals to minus 2, yes. Now, let's summarize our lesson for the jumped piecewise graph. If you encounter such a graph, without checking the three criteria, you can detect simply like this. Now we are going to ask to check continuity at x equals to minus 2. But when you look upward, the value is 2. Yes, the corresponding number for y value is 2. Okay. When you look the corresponding downward for this one, the corresponding value of y is just minus 1. In short, you can avoid now. Automatically, this graph is not continuous at minus 2. Why? Because looking upward and downward has different or distinct values. So looking up and down, it has different values. Sometimes 2, sometimes minus 1. This tells you or has an information to tell you the limit is does not exist. Or indirectly, the right and left are automatically different. But for the 0, for this one, look, for this one, which is 1, the same is true if you come from this one, again 1, then the limit is defined, again it is exists, again if it is exists, the limit is the functional value, no matter for this one, no gap, no hello. But for this one, here is hello, we have here hello. But the corresponding, if you look downward, which is here, I have a red solid, this one. This tells you, so I can conclude now it does not exist. Why? Because when you evaluate from right to 3, from the left approach to 3, and from the right approach to the right, it has distinct values, which means that the left and right limits are different. If they are different, it is not exist. If it does not exist, the limit and the function value are automatically different. That's why it violates criteria 2 and 3. So at that time, we are going to be say the function is not continuous at 3, which means that for this graph, So this is all about the jump discontinuous. We will continue for another part, for part 13.